Welcome to InsectTech's Ethical Hacking course videos. Module Reverse Engineering. In this video, we will go through Introduction to Reverse Engineering, Basics of Computer Architecture, Basics of CPU registers, Basics of Memory and Stack, a glance at few assembly instructions, and Introduction to Disassemblers, and finally we'll have a simple demonstration of cracking a simple application. To start with, let us go through a very generic definition of reverse engineering. Reverse engineering is the process of discovering the technological principles of a device, object or system through analysis of its structure, function and operation. But in our case, we are going to do the same with binary softwares. In our case, we are going to read and understand the machine language of the program using some tools called disassemblers or debuggers. To understand this in a very clear way, let us go through the next slide, where we have a very simple picture which is demonstrating the generation of .exe file from a simple C program. Let us say we have written a simple C program which is sample.c. Once after completing this program, we will try to compile it, which actually gives the .exe file of this source code. Now once after generating this sample.exe, we can simply delete or remove this sample.c and we can execute this sample.exe regardless of sample.c, and upon execution of this sample.exe we will be able to see the output. And this is what generally software vendors are doing. They are actually writing some source code, compiling it, and they are giving us a exe file. So in our case, we don't have the source code to modify the program, to create our own programs using the source. Now this is where reverse engineering comes into the picture. So in a reverse engineering case, we will take this sample.exe file which is actually giving the original output. We will try to disassemble it and we will try to modify the code, and we will generate modified exe file with which we can get the desired output which we want. Now to start with the very basics, let us first try to understand what is a byte and what is a word and what is a nibble. One bit here, 1 is 1 bit, 0 is another bit. So 4 bits is called a nibble and 8 bits is called a byte and 2 bytes is called a word. Now what is the order of a byte? Byte order or endianness. Generally, machines take two types of byte orders. One is big endian format and another one is little endian format. Generally, big endian machine stores the most significant byte first. For example, in this example, 34 is one byte and 56 is another byte. And if it is in big endian format, 34 is the most significant byte, so we have kept it first, and 56 is the least significant byte, so we have kept it at the end. So this is big endian format. The same thing in little endian format is the least byte will be kept first and the most significant byte will be kept at the last. So this is little endian format. This is a representation of bytes. And similarly, we have another example where we have taken 56, 34. We have just reversed the previous example. So in this case, little endian format will become 0x34 56 and big endian format will become 0x 56 and 34. And in our examples, we are using Intel Cross 86 architecture, so we use little endian format throughout the examples. So let us try to understand the basics of computer architecture. We have started with 8086 processors in 1978. It's Cross 86 architecture, the computer architecture, and was called Cross 86 to show that they all ended in the number 86. And we used to have 32-bit processors, and those are called Cross 86 32. This is the representation for 32-bit processors, and for 64-bit processors this is the representation, Cross 86 and 64. And the basic difference between 32-bit and 64-bit processor is the register. Before understanding the difference between these two, we need to understand what is a register. A register is a small amount of storage used by the CPU, where the CPU keeps the data it needs to access the quickest in order for optimum computer performance. Now let us understand the bits. The bit designation refers to the width of the register. It means if it is a 32-bit register, it holds more than a 16-bit register and an 8-bit register. Similarly, if it is a 64-bit register, it can hold more data than a 32-bit register. So this is the width of the register. The bits 32 and 64 entitles the width of the register. So the more ample the space in the CPU's register system, the more it can handle, especially in terms of utilizing the system memory. Now, a CPU with 32-bit register can have a ceiling of 2 power 32 addresses within the register. This is equivalent to 4 gigabytes. Hence, it cannot support more than 4 GB of RAM. Whereas in the case of 64-bit registers, it can have 2 power 64 addresses within the registers, which is very huge. Now let us try to understand the CPU registers. We have in 32-bit architecture 1, 2, 3, 4, 5, 6, 7, 8 registers, and another one is EIP that we haven't included here, which is instruction pointer. Now EAX is the accumulator register, which is used to store the results of our calculations, and this EBX register is not designed for anything specific, but it is completely free for extra storage space. And ECX is the count register. This is a universal loop counter. It functions similar to a variable we use to set up loop counter value. And this EDX is an extension to the accumulator, and it is useful for storing data related to the accumulator's current location. And then we have EBP. EBP stores parameters or variables on the stack. The base pointer holds the location of the current stack frame. We will see what it is. The full form of EBP is extended base pointer. I forgot to tell. EAX stands for extended accumulator register, and EBX stands for extended base register, and ECX for counter register, EDX for data register, EBP for extended base pointer. Now ESI, it holds the location of the input data stream. Whatever the input we are taking, the register is taking, the processor is taking, it holds the location of that input data stream. Now EDI. EDI points to the location where the result of a data operation is stored. In other words, every loop must store its results somewhere, and this destination index points to that place. And finally we have ESP. It is the stack pointer. It always points to the top of the stack. We will see a couple of other registers among these registers in couple of other slides. We will try to have a deeper understanding of what these registers do. And now, when a register is referred to by its extended name, it means you can see here we have removed E in this EAX. So we are in this 32-bit architecture, 32-bit register, we are using E as an extra one. So when a register is referred to by its extended name, it indicates that all the 32 bits of the register are being addressed, and these registers can be broken into similar subsets of themselves, and the first 16 bits of each register can be referenced by simply removing the E from the name. You can see here, this is the AH, which is broken, EAX has been broken into AH and AL. Now additionally, registers, we can just remove this E from this EAX, and we can represent it as AX for the first 16 bits. Now this AX in turn can be broken into AH and AL, 0 to 7 AL and 8 to 15 AH. This AL stands for lower addresses and AH stands for higher addresses. Similarly, the other registers also can be broken into for the subsets of themselves. And now let us try to understand the parts of the memory. We have three parts in the memory. One is code segment, and another one is data segment, and another one is stack segment. This code segment contains instructions that the processor executes. It means the actual program instructions that are being executed by the processor. And the data segments consist of variables and the dynamic buffers. And finally, the stack segment consists of it is actually used for passing the data to the functions. It is very useful. The stack segment is very useful when functions are getting called. We'll see an example of how it works, this stack segment. But to understand the stack is a piece of the process memory. It's a data structure that works LIFO, last in first out. We'll see what it is. And a stack gets allocated by the operating system for each thread, and the stack is pretty fast but limited in size. Whenever a function is called, a limited amount of size will be allocated for a stack by the operating system. Now if you go further to understand the stack, there are two operations which are very, very important on a stack. One is push and another one is pop. Whenever we try to push, an element will be added to the top of the stack. Now we have no elements in the stack, and this will be the top location of the stack. So if we try to push some element onto the stack, the element will be pushed into this location, and this is how it happens. Now we have this location as the top of the stack. So if we try to push some other element onto the stack, element will be pushed onto this location. So similarly, we can push one more element onto the top of the stack. So every time we try to push an element, it will be pushed onto the top of the stack. Simply, in other words, pushing is adding elements to your stack onto the top of the location. Now we have one more operation, that is pop. Pop will remove one item from the top of the stack and it puts in a register. It means if we try to pop the element from the top of the stack, it will be removed like this, and if we try to pop one more element, it will be popped out from the top of the stack like this. So this is how pop operation works. Now let us try to understand what is stack pointer. Stack pointer will always point to the top of the stack. It means if we try to delete one element from the stack, currently the stack pointer is pointing to the top of the stack, which is the top element. Now if you delete this, if you pop this particular top element like this, Now the stack pointer will be pointing to the top of the element. This is how a stack pointer works. And now let us try to understand the stack further. Whenever a function is entered, it means, let us say function A is calling function B. Now we have entered into a function. Now a stack frame is created. This is just some information on the stack, and that is filled in and organized. When function A calls function B, a stack frame is pushed onto the stack. A stack frame consists of stack frame pointer, which is SFP, and return address. This is the location of the next instruction in function A. Because function A has made a call to function B, after completing the execution of this function B, it has to go back to function A. It has to execute the next instruction, and address of that next instruction will be stored in this return address. Now SFP holds, the stack frame pointer holds the location of function A's SFP. It means the function A's stack frame pointer, and the location of the current stack frame pointer will be stored in a register called EBP, extended base pointer. So to be clear, when function A calls function B, it first pushes the address of the instruction after this function call. This becomes function B's return address. Now function A pushes the location of its own saved frame pointer. Now stack frame is almost complete, and then it jumps to function B. Now whatever the code is there in function B, it will be executed. When it is done, it will go back to function A, and this is what a stack frame pointer is. Now let us try to understand some basic assembly instructions which are very useful. The first one is push EAX. This will push the EAX value onto the stack, its accumulators value. Now pop EAX, it will pop the value of EAX from the stack to a register. Now call some address. This particular instruction will make a call to a function at this particular location, which is 0xaddr. It's the address. Now move EAX10. This particular instruction will move this value 10 into accumulator register. Add EAX. What this does is, it will add the value 10 to the value of EAX register, and it will save it in EAX. Now the next instruction is jump some specific address. What it does is, it will jump the flow to a specific address. And the next one is JNE, jump if not equal. It will try to compare some results, and if they are not equal, then it will try to jump to some specific instruction. Similarly, if the comparison is equal, it will try to jump to a specific instruction. Now let us try to understand what is a disassembler. Before understanding disassemblers, let us try to understand what is an assembler. Assembler is a computer program which takes assembly language program as an input, and it generates an output which can be understood by a machine. It is a machine language output. So disassembler is quite opposite to this particular assembler. Disassembler takes machine language program as an input, and it generates assembly language program as an output. One good example of these disassemblers is OllyDbg. This is a very well-known disassembler which is very popular, and we are going to have a simple demonstration with this OllyDbg. Let us try to crack a sample crackme file with OllyDbg disassembler or debugger, and before actually cracking this sample application, let us try to understand what this OllyDbg tries to do. I am opening my XP box where I have already kept my OllyDbg. I am opening it. This is a very interesting tool. Now I have one simple file on my desktop which is ReverseMe. If I try to open this ReverseMe file, it is showing an error which is evaluation period out of date, purchase new license. It is asking me to purchase a new license to run this software. Now using reverse engineering techniques, we have to bypass this error and we have to use this software for free of cost. Now I have taken a sample application ReverseMe. This is a sample ReverseMe application. Anyone can download it from tutsforyou.com. Now let me go back to my OllyDbg. Just open this crackme file from here, my ReverseMe file. I am opening it. Click OK. Now it has opened some nice windows for us. This particular OllyDbg works at Windows application level and can control the applications also. In other words, we can find bugs in a program and can correct the program also. And the left side where this particular window is for virtual addresses. When we load a program, when we run a program, it will be loaded with some virtual addresses. Now these are the opcodes which a machine can understand but a human being cannot understand. And these are the assembler mnemonics, means this is a translation from this opcodes so we can understand this. And this window is for comments, so that we'll be able to understand what this program is actually doing. And these are the registers we have, and these are the flags. Flags generally store 1 bit of data. And finally we have stack window. Now let us try to understand what this OllyDbg does to crack this application we have run. Now when we were running the application, we are getting an error. So first let us try to see the error in this particular code. So I'm just giving a right click and I'm going to search for all the referenced text strings. So now I got all the reference text strings. In that we need the error, evaluation period out of date, purchase a new license. So I'm just giving a double click so that we'll be going to the main window of this error. So I have just given a double click so that now I'm in the main window of this error. Now one thing we have to understand here is we can set breakpoints using this OllyDbg, so that we can run line by line till the end. Right from the beginning of the program, we can run each and every line, we can execute each and every line manually by just putting some breakpoints, so that when we run this program, the program's control will be stopped at the breakpoint that we set. For example, I'm just going to set a breakpoint at this particular address. For that I'm just going to give a simple double click. So it is now red in color. So if I run this application, the flow of this program will be stopped at this particular breakpoint. Let us try to do that. So I'm just giving a click on this particular button which runs the application, and now you can see the application flow has been controlled by this breakpoint. So from here we can run every single line just by clicking on this button or pressing F8. So I'm running every line so I can understand what this particular program is doing. So if I go down, it is actually loading an icon here. I have crossed it. Now next one, it is loading a simple cursor, and then it is creating a file, keyfile.dat, and then we have a jump instruction. Now this is an important instruction here. We have to concentrate here, because if you observe, this is actually checking, comparing something, and it is trying to take a jump. And if you observe here, jump is not taken. So let us understand what happens if it doesn't take the jump. So if it doesn't take the jump to this particular 0040109A, it will go to the next instruction, which is push A, and after that it is actually entering into a block which is loading a message box which is showing evaluation period out of date, please purchase a license. So we should be able to bypass this particular jump. So we should take a jump instead of not taking a jump. So to do that, jump instruction will have a flag Z. So one represents it is not taking a jump, so I'm just going to make it 0. So now you can understand, you can see this message here, jump is taken. So let us go to the next instruction, that is push 0. Let us scroll down, and now it is going wait. Now we have one more jump instruction, which is JNZ to some particular address. Now if you understand here, this jump is not taken, and what happens if this jump is not taken? Let us try to understand. If this jump is not taken, it will execute the next instruction, which is JMP 004010F7. So let's go to this particular address and see what happens. And this is the address, and if it executes, this is going to show one more error, that is key file is not valid, sorry. So if we go up, this particular jump should be taken. If it doesn't take a jump here, it will execute the next instruction, which is directly taking a jump to error message. So I'm just going to take a jump over here by changing this flag Z to 0. So now if I click here, if I press F8, awesome, this jump has been bypassed. Now if I go down, I have one more jump JL to this particular address, which was actually the error message just now we have seen. So this particular jump also should be bypassed. But JL, its flag, Z is not its flag, instead its flag is S, and if you see the message, jump is taken. So if this jump is taken, it will go to the error message. So this jump should not be taken. So I am just going to change this flag S to 0. Now if you see the message, jump is not taken. So we are able to bypass this jump also. So let me run the program again, and now we have gone to one more jump, JE short, which is going to this jump is taken, and it is going to 004010D3 address. So let us go to that address and see what is that. And this is the address it is going to. And after this we have one more instruction, ZL 00401047, and this is actually the error message. And after this instruction we have a direct jump which is actually taking us to 00401205. So let us go there and see what it is. 00401205. Just going down. Great, this is the address, and if you observe, if this line gets executed, it will show you a message, you really did it, congrats. So that we'll be able to bypass that error message which we are getting when we execute the program if we are able to execute this particular line, so that we should be able to execute the jump instruction which is taking us this to good instruction, good message. So what I'm going to do now is, now we are here. Now we should be able to execute this instruction. So for now I'm going to take this jump so that it will go to this JL instruction. So I'm not going to change anything over here. Awesome. Now we have taken the jump. Now let me execute one more line. Alright, now JL short. See, this jump is taken. If we don't take this jump, we'll go to the good message, because the next instruction that is going to be executed is taking us to the good message. So I'm just not going to take this jump, so that I'm going to change this flag S to 0. So if I click it, and if I click it again, just execute the next line, execute. Awesome. See this, it has executed. You really did it, congrats. But the thing is, we have to be able to automate the process. Every time we cannot be here with OllyDbg to execute this particular message step by step. So we should be able to automate the process. So that's what we are going to do now. Let's close this OllyDbg again. Let's close this application and open it again, so that let's try to automate the process. I'm just opening it, and now again let us try to search for all reference text strings and open it. Now let us set a breakpoint as we have done in the previous case. Now execute this. Alright, now go down. This is having a jump instruction over here, and this jump is not taken, so that it will execute a message which is error message. But in our case we want a good message, so that what I'm going to do is I'm going to give the address of the good message to this particular jump instruction, so that it will take us directly to this instruction message. So the address of this instruction is gonna be this one. So I'm just copy this to clipboard and open a notepad file, paste it here and copy the address, close it, and now let's go back to the jump instruction we had here. Let us try to change this jump instruction in such a way that it will directly jump to a desired address, which is a good message. So I have changed this instruction JMP jump to that instruction which is actually producing a good message for us. So I'm clicking on assemble, cancel. Now we have modified the code, and now we have to save the changes. So copy to executable, all modifications, copy all, and now it has shown us a new window with exe code. So save this file as reverseme_cracked. Save it on the desktop itself, close it, close everything, and then try to execute this reverseme_cracked. Awesome, it is showing a message. You really did it, congrats. This is how we perform reverse engineering on software binaries, and this is how we can edit the code, and we can modify the code, and we can save the modified code. And let me go back to my presentation. That's all with this reverse engineering video. Thank you.